So that's a hard talk to follow. MySQL 5.7 and 5.8 have a nice feature set, so I'd look forward to that, but maybe not look forward to following that talk. I'm here to speak about MyRocks, MongoRocks, and RocksDB. MyRocks is a RocksDB storage engine for MySQL. MongoRocks is a RocksDB storage engine for MongoDB. And RocksDB is a key-value database engine. I work on transaction processing at Facebook. I have been with WebScale MySQL for 11 years, RocksDB for about 3 years, and MongoDB for about 2 years. I think maybe 11 years ago, I joined Google and started a MySQL engineering team, and we did interesting work there. 7 years ago, I was recruited at Percona Live by Facebook, joined Facebook and started a MySQL engineering team there, and had the opportunity to do more interesting work. But my biggest contribution at Facebook has been to help grow the MySQL teams between software development and production engineering, and also now to help grow the RocksDB team. We have some very talented people. We give them a lot of opportunity to thrive, and it's just been enjoyable to be part of that process, having started there when we did not have so many resources. When I first joined, it took a few months for me to port crash-safe replication patch from the Google patch for MySQL over to Facebook. And Domas eventually started complaining, what took you so long to give us this fix? Because restoring a slave from backup after it crashed is a bit of a pain. And my response was, you weren't yelling loud enough for that feature. You know, the team is one. I can work on 1 or 2 things at a time. But really, the key point is that we have a strong relationship between the people who deal with production and the people who are building software that run in production. There's a very short feedback loop. If something we build is not working, they will tell us quickly and expect us to fix it. So RocksDB is an embedded database engine, key-value API. This is a fork from LevelDB, but the code has changed significantly since then. The use case for RocksDB is different than LevelDB. We tolerate a more complex code base because we want more performance and more features. If you run a benchmark between LevelDB and RocksDB today on a many-core server with fast storage, you will see the difference between the two. MyRocks is the RocksDB storage engine. Let me get back to RocksDB. The initial use case for RocksDB at Facebook was low latency access to a database on fast storage. So if we have a NAND flash device that can do 100,000 or 200,000 IOPS, it's much easier for us to use all of that I/O capacity via RocksDB than via MySQL, especially when the database is embedded, so we avoid network latency. We don't have a parser or a query optimizer, so if you need to quickly get data from storage into the application, RocksDB was a great fit for that. MyRocks, the RocksDB storage engine for MySQL, the initial use case here is the social graph transaction processing workload. And there was a lot of discussion at the start of the project. What do we need to show that we can do with MyRocks to justify the effort? We've been working on MyRocks for about 2 years. Building a new storage engine for MySQL is a huge undertaking. And so initially, we did some hand waving, and round numbers are nice, so we threw out, let's go for 2x better compression and similar performance to InnoDB. Initially, we verified that from synthetic benchmarks, and we've also verified in production. We are expecting at least 2x better compression And at least for the link bench, I'm showing better performance, not similar performance. So I think we're going to exceed the goals that we set. MongoRocks is a RocksDB storage engine for MongoDB. Within 1 year, we implemented and deployed MongoRocks. The storage engine API for MongoDB is much friendlier to people who want to write a new storage engine. Now, my role on RocksDB has changed. With MySQL, I've been an outsider. I've been free to write about the good and the bad of MySQL. Now I'm on the product side. So some of what I'm doing is marketing. Hopefully, I'll continue to remain reasonably fair. I look forward to bug reports or nice blog posts from other people who have things to say about RocksDB that will help us make it better. Basically, there are 3 reasons for RocksDB, MyRocks, and MongoRocks. The first is performance, and that was the initial motivation. We have fast storage devices. We want the database software to get out of the way when we want to put data onto those devices or get data off. We definitely get much better throughput from pure RocksDB compared to InnoDB. It's easier to saturate, get all the I/O capacity from a fast SSD. And the initial use case required excellent performance. But as we grew the usage of RocksDB within Facebook, people needed features. Sometimes these features make RocksDB slower. Sometimes they make it more manageable, more usable. But a lot of innovation has been done to both make RocksDB performant and to add features. We've added transactions. We have optimistic and pessimistic concurrency control for pure RocksDB applications. We share that code. MyRocks uses it. Backup is an example. We have a merge operator that lets you apply deltas to a key to make the writes cheap, and then the deltas get merged on the read. The last point is what drew me into RocksDB, and it's efficiency. And performance is about how fast you go. Efficiency is about how much hardware you use to go that fast. Sometimes you can be more performant and more efficient, but usually there's a trade between performance and efficiency. So for the rest of the talk, I'm going to speak about performance and efficiency together. This is something that I hope becomes more common as we talk about database performance. There will be a lot of benchmarking and bench marketing between RocksDB and alternative engines over time as this becomes more of a product. So small data at Facebook, we say, or Domas and I call ourselves small data engineers in contrast to big data. The database in aggregate and the workload is large, but the transactions are small. They're user-facing, quality of service, response time are critical. RocksDB in production is handling more than 9 billion queries per second. We have a variety of storage solutions. In some cases, the database is in memory, and I think that was one of the initial use cases. In other cases, it's on SSD or a disk array. MySQL, we have many tens of petabytes of data. The storage in this case is SSD or flash cache. Flash cache is for InnoDB. We use a flash device essentially to extend the InnoDB block cache, only it's a kernel module, so it's transparent to InnoDB. One of the problems we have is that the team has done a great job in terms of scaling the database tiers and providing a high quality of service, highly available database tier. That means we get a lot of users. We get a lot more workload, we get a lot more data. And then at that point, efficiency becomes a concern. If the team had not been as talented, we'd have fewer scaling problems to solve because the data would be elsewhere. We frequently use better performance to motivate better. The previous talk, there was the 1.6 million QPS slide. And so great, 5.7 has better throughput at high concurrency. But performance is only one aspect of defining better, what defines better for a database engine. I joke that performance frequently makes the marketing team happy because then we can write blog posts with the new and better performance. Efficiency is something that I care a lot about. Efficiency frequently makes management happy because last year's hardware purchase will last long enough to handle next year's workload when you are more efficient. Manageability makes the operations team happy. If the on-call can sleep at night because the on-call doesn't have to wake up every time a server fails, then you have a more manageable database tier. We have fast and automated failover for MySQL at web scale. This is something that I didn't think was possible. Very good, well, in much less than a minute, we would replace a failed server. Nobody has to wake up. Usability makes the developer happy. If they don't have to waste time reinventing the wheel because the scalable database is scalable because it sacrificed too many features. A developer should not have to implement two-phase commit in their application when the database is missing transactions. Transactions is just something you have to have if you want to run an interesting application at web scale. And then availability makes the end user happy if the database-backed web service is reliable. So many aspects to defining better. I'm going to focus on performance and efficiency, and really keep in mind that performance and efficiency are related. We shouldn't talk about performance in isolation. Short warning about performance. This is a slide that I've produced many times for I/O-intensive workloads. This has good average performance, but lousy variance. Both InnoDB in the past has had some bottlenecks where it would stall when there were too many dirty pages to flush. I've also seen this with some early stage NAND flash storage devices where the garbage collector was not rate limiting at a reasonable pace. And so you get these gaps in throughput. So if we are only presenting performance as one number, average queries per second, it's easy to hide problems like this. The other issue is if we're only talking about performance in isolation, we don't know whether efficiency is being sacrificed to achieve this high performance. So performance, efficiency, and quality of service, hopefully we can speak about all of those together. So I've given my disclaimer about performance, and now I'm going to maybe violate what I said should be done, but the obvious case, RocksDB is a write-optimized database engine. So with MyRocks, we can insert data into it a lot faster than with InnoDB. And in this case, I was running the insert benchmark, almost 160,000 update transactions per second for MyRocks. It beat compressed InnoDB by about 5x and uncompressed InnoDB by about 3x. The relationship I'm showing here between compressed and uncompressed InnoDB is what I usually see when I run benchmarks. Uncompressed InnoDB is much faster than compressed. That's not useful to me because I usually require compression. So the comparisons for MyRocks are with compressed InnoDB. So the previous result was expected, faster inserts from MyRocks. MyRocks does the faster inserts because it uses less random I/O for writes, and it doesn't have to read secondary index pages for index maintenance. But this result is a bit of a surprise. It wasn't expected. I said when we started, the goal was similar performance to InnoDB, and it's really similar performance to compressed InnoDB because the production deployment requires compression. Here, synthetic benchmark, link bench, which is social graph transaction processing. This is open source. It's based on the production workload. We're getting about 5x more transactions per second from MyRocks than compressed InnoDB when the database is much larger than memory. A lot of work has gone into reaching this point, but it was very, very happy to see this. Another nice result we're seeing from Linkbench is, so the throughput again, about 5x better than compressed InnoDB. What is the 99th percentile response time? And this is for the 2 most frequent transactions from Linkbench. It's about 1 millisecond for MyRocks. It's significantly larger for InnoDB, whether or not InnoDB is compressed. So if you're doing your capacity planning based on meeting targets for 99th percentile response time, the difference in that is actually larger than the difference in throughput. So if you're concerned about quality of service, here's an example where we're actually doing much better with MyRocks. But efficiency is what drew me, or what's motivated me to work on MyRocks. And for me, efficiency is how much hardware you use. And so really, let's normalize the hardware utilization rate by the transaction processing rate. So how much hardware do we use per transaction? And what metrics do I consider? How many random disk operations do I use per transaction? How much data am I writing back to storage per transaction? How much CPU is used per transaction? And then finally, how much disk space is used? And so we see here, this is MyRocks versus compressed InnoDB, 5x more QPS, or transactions per second, from MyRocks. But by every other metric, in terms of hardware per transaction, MyRocks is doing significantly better. So InnoDB is doing twice as many random disk reads per transaction. InnoDB is writing 20 times as much data back to storage per transaction. InnoDB is using twice as much CPU per transaction and twice as much disk space per transaction. Now the compression, the last column, the database size on disk, was the initial motivation. If you use half the disk space, potentially you can double the number of database instances on a server. However, that consolidation is only possible if you have sufficient CPU and sufficient random I/O and sufficient endurance from SSD. And so the fact that we get a 2x improvement in all of the other hardware consumption metrics means the consolidation is much more likely to succeed. And storage efficiency is just, what features are we getting from MyRocks? So less write amplification, meaning we write less back to disk per transaction. The benefits are storage lasts longer. If you're using SSD, endurance is likely to be an issue. Endurance is less likely of an issue when you're writing less per transaction. Or you can use lower endurance SSD rather than higher endurance SSD because write amplification is smaller. Less space amplification or better compression means you use less storage for your workload. And that's what we want from MyRocks. Again, the 20x less write amplification, so compressed InnoDB. This is measured from Linkbench, but we see the same thing in production. Initially, we thought it was about 10x. After some performance improvements to RocksDB, we're now at 20x. 20x more writes to storage from InnoDB for the same workload. Why do we see more writing to storage from InnoDB? First, there's more per row metadata. 13 bytes for the transaction ID and rollback pointer is significant for small rows, but it is a cost for all rows. With a B tree, subject to random updates, the leaf nodes are 1/3 to 1/2 empty. Fragmentation means your database has more pages. There's more pages to write back. The double write buffer with InnoDB, it works as advertised. It doubles your write rate. And then finally, the worst case for write amplification with a B tree is when you have to write back a page because it has one modified row. If the page is 8 kilobytes on disk and the row is 256 bytes, the amplification from that's a factor of 32, and then double that to 64 with the double write buffer. So storage efficiency, we are seeing 2x better compression compared to compressed InnoDB, and 3x better compression compared to uncompressed InnoDB. Again, I usually ignore the uncompressed InnoDB results because I require compression. Big win, and it's what we were hoping for. Why do we see more compression? Well, the first is the per row metadata, the 13 bytes for the transaction ID and rollback pointer. B-tree fragmentation is another cost, meaning the database is going to be about 1.5x or 2x larger than it would be after a reorg. Roundup. So if you're using compression with InnoDB, if the page is 16 kilobytes in memory and 8 kilobytes on disk, if you compress 16 down to 5 kilobytes in memory, you still have to write out 8 kilobytes to disk. Hole punch compression for InnoDB was an attempt to avoid this issue. I have a strong publicly known opinion on why you should not use hole punch compression. I don't think InnoDB can fix this without considering something like WiredTiger, which does a copy on write B-tree. Prefix compression, we get that with RocksDB. We have covering indexes, which have large keys. The large keys are greatly compressed thanks to prefix compression in the data blocks. So why so many engines? I'm a big fan of MyRocks, but I don't think that one database engine, one database algorithm is sufficient. I think we need multiple production quality engines for MongoDB and for MySQL. I don't think one algorithm will be better for both read, write, and space efficiency. It won't dominate all other algorithms. And there's a paper that I'm co-author on that was published this year to talk about that topic. There's many trade-offs that we are making in the algorithm between efficiency for point and range queries. There's a trade-off between being efficient for a range query and for writes, and then finally between write and space efficiency. If you want to make a range query efficient, you need to logically adjacent data needs to be physically clustered. If you're updating data that's subject to range queries, if you update the data in place, as is done for an InnoDB B-tree, you see you make writes inefficient. You increase write amplification. So that need to cluster for range queries makes updates or writes more expensive. So there's a trade-off we have. RocksDB makes writes cheaper by potentially making reads more expensive. You might have to look in multiple locations for a read. We reduce that cost with a Bloom filter for point queries. Bloom filters don't work for range queries, so there's the potential for range queries to be more expensive with RocksDB. At least for link bench, we're not seeing that cost, but it is possible. And then finally, there's the tension between write and space amplification. If you think of garbage collection as a process that reduces space inefficiency, every time you run garbage collection, you are increasing the cost of writes because you're doing write activity. And so you can be efficient in space by garbage collecting frequently, but that has the impact of that is writes are more expensive. Where might RocksDB thrive? You might be motivated by hardware. You might be motivated by workload. For me, I've been motivated by hardware. I want more compression. I want better SSD endurance. If you're using a disk array, RocksDB can be a good fit. It uses less random I/O for writes, which means it saves more random I/O capacity for reads. You can also be motivated by workload. If writes are frequent or point queries are frequent, then it can be a great fit. But you don't have to match all of these criteria for RocksDB to be a good fit. Innovation. The RocksDB team has been very productive. We have mailing lists. We have a lot of wiki pages that explain these. We are happy to discuss these features on the mailing lists or the Facebook groups, also in the booth. but just a lot, it's hard for me to follow at times. A lot of work has been done, and a lot of work is in progress. The exciting thing for me is to get MyRocks in production. This is in progress. I can't say it's in production today, but it is going to happen. For you, the exciting thing is to get MyRocks and MongoRocks into a distribution that's supported that you can use. The distribution providers are here, MariaDB and Percona. I hope you speak to them if this interests you. Finally, tiered storage. I'd like to use a combination of fast and slow storage, NAND, flash, and disk arrays, for example. We have 2 features in RocksDB to do that. We have a read cache that uses a storage device to extend the block cache, and then we allow different levels of the LSM, log structured merge tree, to be put on different storage devices. We have plans to get server-side Lua. Initially, this will just be for pure RocksDB, but I would like to see something similar to Toronto that lets us put business logic in the server via Lua. And then there's a lot more. So please join us, rocksdb.org. We have mailing lists. We have a Facebook page or 2 Facebook pages. We are happy to discuss this with you. Thank you.